Greetings! Through our class, Language Trends Through Statistics, we've learned how to think like a quantitative researcher and how to conduct research that numerically describes linguistic phenomenon. Today, we'll be discussing the importance of understanding statistics within the context of second language acquisition by delving into the 5 core inferential techniques fundamental to quantitative research. But first, let's clarify what we're talking about. Statistics is the field of measuring and interpreting data in order to prove or disprove a point. Understanding statistics allows one to analyze and interpret numerical data, fosters critical thinking, and enables one to acquire statistical literacy, i.e., the ability to understand, conduct, and critique research. Here's the basic frame needed when conducting said research. First, we formulate both the null and alternative hypothesis. The null hypothesis is the assumption that there is no effect. The alternative hypothesis is the assumption that there is a statistically meaningful effect. Then, we set the significance level and conduct power analysis. Then, we run inferential statistics. Then, checking the data, we choose whether to reject the null hypothesis or not. Finally, we make a report on the various important statistics. Of course, we should always be careful of reporting on an error. There are 2 types of errors, type 1, alpha, and type 2, beta. Type 1 errors, better understood as false positives, is when we mistakenly reject the null hypothesis and say that there is an effect when there is none. The significance level, or alpha level, represents the risk of making a type 1 error, with an alpha level of 0.05, meaning that there is a 5% risk of error. Type 2 errors, better understood as false negatives, is when we mistakenly reject the alternative hypothesis, saying that there is no effect when there is one. We check this via the conventionally accepted maximum beta, usually set at 0.2 or 20%. In that case, we'd want to be 80% sure that we can detect a real effect. Now, let's talk about the 5 core inferential techniques fundamental to quantitative research. The first is t-tests. T-tests are a statistical method that helps one figure out if the difference between 2 values is real or just coincidence. There are 3 types. Independent sample t-test compares the results between 2 different groups. Paired samples t-test compares the result of a single group but at 2 different times. And finally, one sample t-tests compare the results of a single group to a known value. Before conducting t-tests, however, there are also several assumptions to be checked first. First, we check if the dependent variable is a continuous variable. Then, we check for normality by using the Shapiro-Wilk test or looking for a bell-shaped curve. Then, we check for the homogeneity of variance by using the Levene's test. Last, we check if all the data points are unrelated to one another. If all assumptions are met, we conduct a parametric test, for example the independent sample t-test. But if they are not met, we must conduct a non-parametric test. If homogeneity of variance is not met, we use Wilk's test. If normality or all assumptions are not met, we use Mann-Whitney's U-test. When using t-tests, we should report on the following stats. P-value, i.e. the chance that the null hypothesis is true. If it's below 0.05, it tells us that the data is significantly significant and that we can safely reject the null hypothesis. T-statistic, i.e. the standardized score. Degrees of freedom, i.e. how many values in our data we are free to vary. 95% confident interval is the range that we can be 95% confident contains the true population mean. Effect size, i.e. the magnitude of the difference between the 2 results. Using Cohen's d, we can measure just how meaningful the result is. Now, let's next look at a non-parametric test. The t-squared test is used to examine whether there is a significant relationship between two categorical variables. While as a non-parametric test, we do not assume a normal distribution, there are still several assumptions to be checked. All data must be independent. The two categories must be mutually exclusive. Last, the expected frequency in each cell should be ideally be more than 5 or more. Now, there are two types. A goodness of fit test is used when there's one categorical variable with more than two levels within. It helps determine how well the sample data matches distribution. An independent test is when there are two categorical variables. It helps determine whether there is a relationship between the two variables. The effect size can be measured using two possible tests. Phi is used on a 2x2 grid, while Kramer's V is used when the data exceeds the 2x2 grid. This all helps determine the likelihood of a relationship existing. Now, we can check the strength and direction of this linear relationship between two continuous variables by using the Pearson's correlation test. The assumptions when running a correlation test is that all variables are continuous and both are normally distributed. They do not have to be independent nor dependent. It is reported using Pearson's correlation coefficient, or the R value, and ranges from 1 to -1. 1 suggests a positive correlation, -1, negative correlation. The closer the R value is to 1, the stronger the relationship is between the two variables. Meanwhile, 0 suggests no correlation. We check for normality using linearity and homoscedasticity. Normal linearity suggests the relationship between the two variables should be linear and can be seen on a scatter plot. Normal homoscedasticity suggests that the spread of data points around the regression line stays roughly constant. For this, we can see it via a residual plot. When normality cannot be assumed, we can use non-parametric alternatives instead. Spearman's flow is used when we only have the data ranks and not the raw data. Kendall's tau is used when we have small sample size and many identical scores, or when the two variables only have ordinal scale levels. Expanding our relationships, regression is when we reduce equations in order to predict potential data. Simple regression only checks for one independent variable, or predictor. Multiple regression checks for two or more. The equation is as below. The dependent variable is equal to the original data point, or intercept, plus predicator times slope. When dealing with multiple regressions, we simply add more variables to the end as such. The assumptions when calculating regression is linearity, homoscedasticity, normality of residuals, and multicollinearity. Expanding on above, normality of residuals can be found in residual histograms or QQ plots. Multicollinearity is assessed via VIF, as shown above. When checking our regressions, we can use model summaries, coefficients, and ANOVA. In a model summary, we can see how much variance there are in the dependent variables. R squared explains how much the models/predictors explain the outcome using percentage value. Adjusted R squared is R squared minus insignificant predictors. Coefficients give us our intercepts and slopes for the equations shown before. When unstandardized, we can see exactly how much one variable can affect the outcome. When standardized, we can directly compare the differences between one another. Finally, we have ANOVA, short for Analysis of Variance. It measures the significance of differences between 3 or more groups and helps clarify if the differences are to be attributed to outliers or if there truly is a statistically meaningful difference. There are 3 assumptions when using ANOVA. The first is independence. All 3 or more variables should be separate from each other. Next is normality and homogeneity of variance. When these assumptions are not met, we use non-parametric alternatives. When normality is violated, we use Kruskal-Wallis. When homogeneity of variance is violated, we use Welch's ANOVA. The reason we use ANOVA instead of multiple t-tests is that the more t-tests we use, the more likely we'll have an alpha error. ANOVA is checked via an F value. An F value is when the variance between groups is divided by variance within groups. The bigger the F value, the more likely it is that there is a statistically meaningful difference between the 3 groups. The effect size can be checked using omega squared. The sizes are as follows, with small being 0.01, medium being 0.06, and large being 0.14. After using an ANOVA test, you can further check using a post-hoc test. The parametric post-hoc test is Turkey's HSD. The effect of turkeys can be checked with small being 0.4, medium being 0.7, and large being 1. This has been a comprehensive review of the 5 core inferential techniques fundamental to quantitative research. We hope we were of big help in explaining the nuances of statistics, and we wish you all luck on your finals.